of physical design. So I have been trained, so I know some of the areas where I can give some knowledge to everyone. So everyone are aspiring to get knowledge right now and looking for jobs, right? So this would help, I guess. So let's not delay. We'll just start right now. Okay. Before going anything into particularly into physical design, I'll just give an overview so that before entering into anything particularly, we should have the basics or overview so that how the things work. So we'll start with the flow. So if a chip needs to be designed, how it happens and where it ends. Okay. So the first thing is RTL design part. So here you can see on the flow design flow here that the first thing happens is MRD, that is market requirement document. That is a company. If it's for a client, then a company, or if a client provides some requirements to the company. For example, we have Intel. So a particular company comes and asks Intel to manufacture a chip which performs on certain clock frequency, which operates on certain frequency range and other certain power limit and everything. It will give some design requirements. So and it asks it to do the chip manufacturing in certain nanometer of technology. So what does the Intel do? This Intel takes all those required documents just as a brief, because certain companies doesn't provide complete design specification. They just give the required document. So what does the client is asking? So some companies provide the details. So this Intel, the main preparation goes here. Like the main company is Intel, which is going to manufacture, right? So that is going to start working on it. Just I'm giving an example. Consider it as an example. So when it starts from market research document. Once this is acquired, then it will be moved to design specification. Means they will design everything from the scratch. Means if they will start to do as per the requirement, they will divide everything and they will focus on each block and they will start to work. It's like if a chip needs to perform some ALU, arithmetic logic operations, arithmetic logic unit with arithmetic operations, they will divide the block. For example, they might divide the block as additional block, subtractional block, a multiplicational block, or a division block, or modulus, etc. So those will be design specific. So when we go to additional block, the block that does the addition part, the design will be different. But when it comes to subtraction, the design varies. So the design for all the blocks will be different. So like the design specifically, it will be divided. Then we get into the block and do the architectural definition. Here, the complete design of that block will happen. Means the additional ALU block, in ALU, the additional part, addition design block will be start to working. So that specific architecture will be done for each block. The starting, they will design as a block. They'll define it as a block and then they'll start to design. Okay, in microarchitecture, it will start to do with two things. For example, considering additional block, you have a addition. Okay, addition of two numbers, addition of three numbers, addition of numbers without carry, addition of numbers with carry, and some in depth. If it goes, it can go like addition of binary numbers, hexadecimal numbers, octal numbers. So in particular, that the micro architecture will be designed. That is, addition is a main architecture. In that, addition of two numbers, three numbers, addition with carry, addition with sum, addition with carry, and addition with other things will be considered as a micro architecture. So I think you might get an overview now how the things are designed. Okay, then it will be moved to RTL design. Now it is defined, so now it has to start to design. Now what does the thing happens is that RTL designers will come into play. They will start to design each and every single block by writing the codes. They will start to write the codes for each and everything, and then the block gets designed. Okay, so this part is RTL design. So some of the design engineers would do this, like RTL design engineers. They will write behavioral or gate level code, or even the data flow code and they'll start to do the RTL designing. So that with that designing, they will make the basic substrate, like the blocks or the basic things for the flow to continue. So after this, the same thing will be given to the RTL verification. Okay, now the RTL engineers have done it. Yeah, we agree. But what happens in the RTL verification? The thing is, they will verify. RTL designers might not be perfect all the time, or there might be some human errors or some errors, and logically there might be some things or some design goals needs to be met. So what happens is that RTL verification engineers will start to verify. They will consider each block, they'll pass some input, they'll get some output, they'll try to verify the design there, or they'll try to meet the goals, whatever the design goals. Like if addition block needs to be performing addition, they'll try to check that is this design working correctly, or is this correctly made up of. Okay, then that after design is met, we'll go to synthesis part. If the design is not met, we'll again come back to RTL design part. So there we'll do the RTL designing. So now you might be having an idea that design and verification engineers, right, as an RTL design verification. So here comes the thing, that is, in RTL design, the design team will be working. In RTL verification, the RTL verification part team will be working. So these RTL verification team will verify the design done by the RTL design team. Okay, now the chip is not ready, only the blocks might be ready. So now even here, after this, there are some areas where layout engineers might come as per the flow, but I'm not considering all of that. I'll consider them as a design part only. We can add a layout engineer here. In design, we get so many people like some low power IC design engineers, layout engineers, many others. So we'll not consider them. We'll consider them, all of them, as design engineers. Okay. Then after moving from here, the thing is, whatever we get, we'll be moving it to the synthesis part. What happens in synthesis is that we will have one DFT insertions. DFT is for testability. The design for testability will be inserted. Means some scan change will be inserted for the data that is coming from RTL verification. Why this scan change will be inserted is that to do these scan change will help in future for the next stages to verify the design. I mean, to verify the logics and all. Okay, here logic synthesis will happen. What happens in logic synthesis? There's a 4 stage. Okay, your data will be like, the thing will be in the file, in a single file after the RTL verification. That file will be converted into a netlist here. What happens? You will get an RTL code. That RTL code will be converted into a diagram, that is like a kind of mapping will or translation will happen. RTL code will be translated into gate level translation. Then the mapping will happen. Means which pin needs to be connected to where. Means like if there is an AND gate, the input of the AND gate is drawn from some other gate. So that will be written in a code manner. That will be converted into a diagram. Means kind of gate manner. So after that, there will be one optimization state where this whatever the mapping is there, that will be optimized and logically corrected, so that it is optimized and reduced. There are no lengthier wires to be connected, or there are no illogical connections are there present. So that happens in the logical synthesis. After that, the scan change will be inserted. We'll talk about scan change in the further topics. For right now, scan chains are those which are used for the verification kind of thing, some to meet some timing or functionality goals and all. Okay, then we'll get a netlist here. What is called as netlist is that gate level netlist. We call it as GLN. Okay, gate level netlist is that the flow will be, whatever the design will be there, that will be converted into a gate level, where every gate is connected to each other, which is providing a combinational or a sequential circuit. that is designed to perform a particular task. Okay, so if anyone asks you about what is gate level netlist, you can say gate level netlist is a nothing but a output of a synthesis, or it's a converted form of RTL where it has some particular gates which has some inputs, and we get a particular output because the gate level netlist has a design which is specific to perform a task. Okay, so from netlist we get, after this netlist is there, we'll do some checks here. Now the logical equivalence check will be done, means the logics will be checked here. So you have this file, so the logic will be checked, like means if you have the gate AND gate, the AND gate logic will be checked, means what's the AND gate logic. If you are giving similar inputs, that's 0 0, you need to get the output 0. If you are giving 1 1, you need to get the output 1. If you are giving a different 1 1, yeah, 1 0 0 is 0, 1 0 is 0, 1 0 1 is 0, yeah, that's the AND gate. So that logic will be checked in AND gate. So everywhere the gate level logic will be checked in the logical LEC. Okay, from there again we are getting a netlist. Okay, this netlist will have the logic check, DFT insertion, everything. So now what happens is that the STA comes. Okay, now the STA is, you might be wondering what might be the STA. Just in a just to tell about it in a sentence, STA is nothing but static timing analysis. So in the word it is saying that it is a static timing analysis, means it's checking the timing analysis which is static, means it doesn't change upon many factors unless and until you are externally influencing something for that. So there's a timing analysis done. Just consider, leave the static, we'll come to it in the later stage. Just consider it as a timing analysis. Why we need to do STA? Because the MRD, whatever you have seen here, right? The MRD, in MRD, there will be a specific thing that this IC or this chip needs to be performing some particular task in particular time duration, right? So at that time, the time comes into play. So this time needs to be considered. So if a particular task is to be performed, if it is not performing within the time, this STA, timing analysis, will check it. Okay, before layout is happening, the timing analysis will happen, means this is pre-layout STA. So the timing analysis will be done. Okay, then it will check, then it will go for the timing goals. Means if, for example, if a particular, I will consider the same thing, addition of two numbers. For addition of two numbers, it should complete within a 4 seconds. But it is not happening, means if it is going beyond 4 seconds, 4 nanoseconds, in terms of nanoseconds, I'll say, because that's somewhere the working area. If it is going beyond 4 nanoseconds, we will mention it as a timing not met. Okay, so that will be reported to the engineers here, those who check for the STA engineers, those who check for the, those people will be checking it and reporting it to the higher engineers. So what happens is that if the timing goal is met, then only we can move to physical design area, physical design part. If not, we'll go back to again logical synthesis and DFT insertion. Here again, if we, why it is in synthesis stage, again in logical synthesis plus DFT insertion, again it will be checked. Why is this thing is not meeting, or why is this thing not going to meet? If there is any optimization chance where a gate needs to be connected in another way, or where a gate needs to be replaced with another way. For example, an AND gate might be replaced with a NAND gate to consider the same logic with another inverter to make the same logic with some time duration variation. Some kind of alterations will be done here in the logical synthesis, and then again the netlist will come out. The same process happens until the timing goal is met. This process is going to repeat again. So once the timing goal is met, we'll get the same netlist GLN. Okay, this netlist, okay, I forgot a thing here. See, you will have this after synthesis, you will have a GLN, right? That GLN will be compared with the RTL design. That is the RTL code. See why it is compared? Because it is compared so that the design is the same. The GLN after logical synthesis and RTL, the code, RTL design code, whatever the code we get, that is Verilog code, will be compared because it's to make sure that the both are the design are same. Like there is no majorly uh, changes of the design. The logic needs to be met here. Okay, so that's it. From there, we'll come to physical design. Now, this is the main interesting part. Before talking about physical design, I'll tell few things for physical design, like some inputs for physical design. So one thing for the physical design will be GLN, that is gate level net list, which you get from this. Then we'll provide some libraries. Some libraries to will be given. That is timing library will be given because we are going to play with the timing, right? So this is the STA stage, the APR, LEC, parasitic extension. These all are STA stage because we have done a pre-layout STA here, and here we are going to do the STA. So this is a timing library. So then we'll go and provide a technology file, that is .tf, we might call it as a technology file. We might even add a def file, def file, and some SDCs. If you are working on a Synopsys tool, you might provide a Synopsys design compiler. And if you are going with the other inputs will be there, like TLU plus and NDM. NDM is new data model, that is also for the Synopsys tool, that is ICC2. If you are using ICC2 compiler, NDM comes into action. Okay, so these some 9 inputs or 6 inputs will be provided based upon the requirement. So that input will be given here. That's where the physical design starts. So here the first part will be APR. What is APR? Automatic place and route. So the thing is placing and routing. Routing means connection of blocks. Placing means placing the blocks in a particular area or particular manner so that the routing happens. Okay. Before I continue this, I'll move into the next slide so that it gives you a brief idea. Okay. Okay. Not, yeah, here we are. Like the implementation, how it happens is that, see, I have said it in previous slides only. In pre-layout STA, after that we'll come to APR flow. This is where APR is. APR has few stages where the first thing is, I'll tell you in the next slide. Yeah, there is a two types of implementation. That is two ways of designing a chip. One is full chip layout. Whatever you are seeing on the screen is full chip layout. One is partition floor plan. Okay, this is the one. So it depends on the complexity of the chip, how you design the thing. There are in flat implementation you use full chip because the complexity will be very less. But when you come to hierarchical flow, partition floor plan, you might use this. I'll tell about this thing only, the hierarchical implementation. Now, whatever you are seeing is the partition flow plan. Just don't get scared because of seeing all of this. This is very simple. It might look hard for you right now, but just go through the flow. Okay. Thing is, this is a chip. Okay, whatever the thing you see on your processor in any, if you open up any old system, you might see a processor, Intel Pentium inside. So the chip might contain the similar kind of photo or similar whatever you are seeing here. So thing is, this there will be a block of certain size, like some width and length. The width and length will be considered as an aspect ratio. Means if the width is 2 centimeter and height is 2 centimeter, it's a 2 is to 2 and 2. That is aspect ratio will be 1. That is the width and height are same. If it is 2 is to 4, that is 1 is to 2. The aspect ratio will be 1 is to 2. So this will be again coming under APR flow in the future topics if you are going to learn. So here what happens is that in this block, each block will be divided. Okay, each area will be divided. So this is a quad pin IC where you can have four where the pins are present at all the four sides. You can see here these the things whatever you have is are the pins, like the upper one, the right and left and bottom. All of these are pins. Okay, these corners are not considered for the pin because you will not have the connection area here. You can't connect a pin to any of these blocks. Okay, this area in the full chip will be empty like this. You can place anything in this, like the RAMs and standard cells and all. But I'll tell that in a partition floor plan, this entire area will be divided. Okay, from here the actual APR starts, the automatic place and route. Okay, so one block will be done. Each block will be done 1 2 3 4 5 6. Okay, to say about block, I'll tell some blocks. This is a rectangle, this is a square, rectangle. So this block is whatever the block 6 you are saying. This is the rectilinear block. We call this block as a rectilinear block. So in this, what happens is that you are given a single block. You won't design the entire chip. Some team will be doing one block each. Okay, so some team will be doing a block 1, some team will be doing the block 2. What's inside the block 1, block 2, I'll say it in another way. Okay, you can see it here that the blue things, the black ones, you can see these all. So this is where it happens. So after the block is done, the partition is done, whatever this thing is divided, right, the blocks are divided, this thing is called as partition. This happens in the APR flow. The first step is partition, then the floor plan, what we call the next step. In floor plan, what you do is you will be given certain memories, certain ALU logic, something and all. That will be a block that you need to place inside the block. Inside the block, if you are consider this as a block, I haven't shown a block picture. Consider this thing as block. So if this is a block, I have to place the macros inside the block, standard cells inside the block. So first thing you place is macros. You give sufficient space between the macros so that you don't have to face the congestion between the macros, because the macros will be communicating with the pins around them. So if you are placing macros one upon the other, the things might get complicated because they can't communicate, and there will be a congestion present. Okay, to communicate and to power them, you need to provide a power line. So that is the next step. That is power planning. So you will provide a VDD and VSS lines horizontally and vertically. So on the metal layers, because you don't design a full chip on a particular area, so it will be divided on a layers. The basic layer will be, for example, I designed one. I worked on a chip where the design was of 7 metal layers. The basic layer, metal layer was the pins and all. The first metal layers was standard cells. Second was the power for standard cells. Third and fourth was for third was and fourth was for some pin and again some macros and all. Fourth, fifth, third was, and fourth, fifth was for clock tree synthesis. CTS, clock tree synthesis, where you will provide the clock lines. And fifth and sixth were for power, where for the PG rails, whatever I said, right, power planning. The fifth and sixth VDD and VSS were drawn on fifth and sixth metal layer. So the fifth and sixth metal layers will be there. These macro standard cells will all tap the power from fifth and sixth metal layer. Some standard cells, not all the standard cells. And for particularly standard cells, the metal layer will be 2, which provides the power. Okay, once the floor planning is done, floor planning is nothing but placement of macros. After that, you will design the power plan, where you will have the power supply VDD and VSS rails. After these two, the third one will be the placement. That is, you will insert the standard cells inside the block where you will the standard cells will be inserted. Like it will be done in the 3 stages, like pass and the legalization. The first pass is that you'll inside the macros, inside the block, near to the macros. Some standard cells communicate with certain macros, so they are placed nearby so that their connectivity length is not increased, which will again cause a issue as of crosstalk. So to avoid that, some will be placed near the macros. In second phase, where the macros standard cells will be rearranged again near the macros. That happens because the standard cells will shift from one G cell to another G cell. G cell is again another topic. We'll talk about it in later stages. So these standard cells will communicate with the macros, and the legalization is that the standard cells will be placed in final way. This happens in the placement stage. The first will be partition, second will be floor plan, third will be power plan, fourth will be placement, fifth will be the clock tree synthesis. Means the every standard cell and macro on the block will have the clock. So everything needs to be connected to clock because this is a synchronized circuit. Like this is a synchronized thing. So it needs to work with the synchronous thing, that is clock. So clock synchronizes all of these things. So we use the synchronized clock and design this. So that is why you need a clock tree synthesis. Clock tree synthesis means it's a process where the all the macros and standard cells are connected to clock. That happens through clock routing. Routing is nothing but connecting the macros and standard cells to each other and to clock using a particular path. That's clock tree synthesis. That's called as routing. And if you use the clock for that to connect the clock with everything, that's called as a clock tree synthesis. So after this comes the routing. So in routing, again, the same thing is you are connecting clocks, you are connecting power, but you are not connecting signals, right? To communicate with one macro to other, you need a path. It sends some data, receives some data. To do all of this, you do create a path that is called as routing. So this routing will be the final path. Once the routing is done, you might, there are errors coming up in the thing here, like these thing block inside. You are all the thing what you are doing is inside the block. The block to block communication will be done by the higher engineers. At the starting stage, you don't need to worry about the block to block. You just need to worry about the pins that are present in the block. So macros and standard cells present inside the block will be communicating to the pins here. So the same way block to pins. So if the communication between block 1 and block 2 needs to happen, that will be done from some other engineers who will connect this block 1 and block 2 or interface all of these to each other so that they communicate and perform the task in a synchronized manner. Okay, so this is what APR flow is. So this is not the end of PD. There is something more here. So this happens, everything happens in APR. So once the APR is done, once the routing is done, again we do the LEC check. That is a logic equivalence check. Means that after APR, your netlist will be modified somewhat. So that netlist will be compared with the LEC again. The netlist from the logical synthesis. So these two netlists will be compared. Again, they will check for the thing like, is the design remaining same or is the design altered? So the design won't be altered because you are just developing it, you are not modifying it. So you are developing at every stage. So that will be verified, and then we go for the parasitic extraction. What happens in the parasitic extraction is, I'll just tell it in a brief way. The R and C will be there, the R and C components, that is resistance and capacitor components. You use the metal layers, right? So in that there are some situations where your metal layers might get short and there might be a coupling capacitance and resistance and all present there, because you are using the transistors. So whatever, if you consider a transistor, the load will be always a capacitor. So these things will come into action. So that is all considered in parasitic extraction. And from there, that there is a file created. That file will be given to the post layout STA. The difference between pre-layout STA and post layout STA is that in pre-layout STA, you won't have the actual clocks acting. You just assume a clock of this frequency and you will design. So in post-layout STA, you will have the clock designed already. That is done in the APR, because in APR you'll do the clock tree synthesis, so that CTS, after CTS, whatever you are getting, that that will be the actual clock. So along with the parasitic extraction, the routing, clock tree synthesis, everything will be considered, and with that we'll do the post layout STA. So in this, again, you need to meet the timings. If timing is not met, go back to APR, again work on it, try to optimize it, meet the timing goals, and come again. If not, you have to do the same thing. If it is met, you'll go for the physical verification. What is physical verification? Here everything will be verified, like whatever you do in the API design is met, whether the blocks are corrected, if there is any optimized way to do it, all of this will be done. And DFM, here design for manufacturability and OPC, optical proximity check. So these things are these things take more time to explain, but in brief, they will check those parameters. Where is this IC or a chip fit to be manufactured, and does this IC have the proximity effect, or will it be able to sustain the proximity effect? Proximity effect is that at some temperature or some areas chip might work different, or at some areas it might work different. Means if the proximity check is passed, means chip can function at certain stable or certain way at certain range of temperature. Means that is how the OPC is done. Means if it is can this chip perform in a constant manner from -10 degree to +10 degree? Considering it an example, I'm giving an example. Will it work in a consistent manner? Yes. If it will work in a consistent manner, then OPC is passed. That is optical proximity check. And in certain areas also, means all around the globe, will it work the same? That is the same thing, that is related to the temperature. And DFM is, yeah, as I said, this chip fit to be manufactured. Then after that, the chip will be sent to the tape out. Like the file that is going to generate after DFM and OPC will be GDS2. That is the file that is going to be generated. That will be given to the tape out engineers. That is like that will be given to the fab, where the fab will tape it out. Like they will take the data and they will put it on the fab unit. For example, the TSMC fab does this thing, and even some other fab units which have their own fabrication units like Intel and other. So this is where the physical design engineers part is to start from APR. Some design engineers part will end after APR, but most of all engineers start from APR and end at STA. Most of all engineers, because there will be a separate physical verification engineer. You don't need to worry about physical verification, DFM and OPC. But yeah, it starts from APR and ends at STA. So after that, the tape out happens. Once the tape out is done, you are happy. You are done a great job. This is all about the flow. So this is very important to know that how the things works here. So from the market required document to tape out, this is all it happens. Yeah, there are other steps included in this. There are other process included in this. I just gave a overview of what happens, and the most happening process or most happening flow. I have briefed it out. And to just give you the idea about how it goes, I'll show some report. The main thing what an PD engineers have to do is, apart from the APR, whatever you are doing, you have to check for the reports also. For example, this is a clock report. You can see here, report clock QR. This is a design named as Laksha. I did it on September. This is date and all. So area. So if you hear the clock, whatever you are seeing, right?
I think your screen is not visible.
Sorry. I didn't share it. Yeah, I think it's visible now. This is a report where a clock report. You will have this. You will have the scan clock. I said right, DFM. This where DFT insertions. Scan change will be there. Scan clock. This is all about clock, where you have the cell count, clock standards, everything. This is the report. For example, you need to understand means this is a report. Just to say you everything, I can't go deep here. This is how the report looks. Here we have repeaters. Clock repeaters are those which connect the clock route from one macro to other macro, or one center cells to other center cells. The clocks where it needs a repeater to convey the clock signal. Like you can't connect a long clock because there will be a skew generated in between them. So these clock repeaters, everything will be used. You can see SCH, SCH buffer 1. These are all buffers. So these are buffer and inverter means inverter insertions will be all done in the clock tree synthesis, the CDS and routing areas. Yeah, you can see inverters, INV, INV5. The inverters change, and here you can see HVT 40 and all. These are very important in future because HVT and LVT cells are more important. High voltage threshold and low voltage threshold. You just check this out on Google. You might get an idea. But HVT and LVT cells are more important for STA, that is static timing analysis. And SVT are the standard voltage threshold, means the threshold will be standard. I'll tell about HVT and LVT in the future stages. Yeah, this is how a report looks. You have to analyze these reports, and in some ways you have to analyze the cell count also, clock cell count, and repeaters, and why the repeaters are more. You have to reduce the repeaters also. This is just a report. There are many more reports you have to always check when you are working on a physical design. At every stage you have to look at the reports and analyze and have to take up the next step. Yeah, you're not alone who is going to do, but yeah, you have to do it with the team. So when you are doing, you have to discuss this, and you have to if there is any errors, if there is any correction needs to be done, you have to report it to your higher engineers or managers who will take care of it. Your task will be to design from APR till STA. When you start to do, you have to look at the reports and do. And the best part of PD engineers is that when you start with the APR flow, you will run certain codes. So when the code starts to run, you don't have any work to do. So you can just sit and relax. But when the code is run and you are getting errors, and the errors in the kind of block, or if you do need to do the correction, you have to do. This is the best thing. The worst thing is if you do a mistake at once and realize when the run is happening, or realize in the middle, you can stop the run. But if you don't know, you have done a mistake, but if you don't know what the mistake is, you have to wait till the run is complete. Only then you will get to know that where you have done the mistake, and again you need to rerun to get the mistake rectified or corrected. So this is time consuming. So you get worried, hectic, and everything when the tapeout is about to arrive, and at that time you don't have enough time. So that's when the difficult thing happens for the physical design. Apart from this is very interesting and best thing here. Even it doesn't matter what nanometer technology you start to work, gradually you learn everything. From certain nanometer technology to a particular level, the flow, everything remains same. After some nanometer technology, you will the things changes, but you can adapt to that. So this is everything about what I have. I can brief right now for the particular time duration.
Yeah. So what is the major changes we can observe from technology to technology?
Sorry, major.
From changes observing from 3 nanometer to 5 nanometer, 7 nanometer.
Yeah.
Technologies.
You have any idea about nanometer? What's the nanometer thing?
Yeah.
Yeah. What's it? I'll try to make you understand why. What's the difference? But before that, I'm asking. You have any idea about nanometer?
Yes, the source to drain length is nothing but a technology.
Right. You got it. So the source to length will be the nanometer technology, right? How can you wait? Is everyone able to see my board? Just a second. Okay. This is thing. See, you have this thing, right? This is the length. What you are going to say? This is, for example, 40 nanometer. You will have this as 40 nanometer. When you are considering the same thing as 10 nanometer, okay, here the thing is for 10 nanometer and for 40 nanometer, the major difference, if you can barely identify, is these two things. That is the channel length. Apart from this, for 40 nanometer, you might give some if you are considering HVT, that is high voltage threshold, means the threshold will be, for example, if the threshold to activate this is VGS, should be greater than threshold voltage, right? VGS should be greater than VT. So you can set VT as 1 volt. Consider VT as 1 volt. VGS should be more than 1.1 just to create the channel here, right? To create this channel, 1.1 needs to be. This is, I am talking about enhancement mode MOSFET. Enhance mode MOSFET. Okay. Here, the thing is. So if VGS is greater than VT, your channel will be created. Again, you need to provide VDS, drain to source current, just to make the flow. But if you change the HVT to 3 volt here, HVT means high voltage threshold, means you are changing your the threshold voltage to 3. If you give 1.1 as VGS, it's not going to work. You need to give 3.1. Okay. So this can't be achieved in higher nanometer technology. For example, 40 nanometer technology. Why? Again, you need to go with the basics of CMOS. I'm not going to touch. Okay. For example, what's the difference means? Technology means if you go with HVT or LVT, you can't achieve the at certain nanometer technology. For example, you can't achieve it on 180 nanometer technology. So you don't have the things as HVT or LVT in 180 nanometer technology or some other technology. Okay, these HVT and LVT come into action in some nanometer technology. So that's why whatever the chips that are going to design in your electric vehicles to do that thing, whatever, like to avoid impact, to accident detection, automatic driving and all. So those cruise control and all, for that they'll design a chip that is going to be at 180 nanometer because they have space. They can design a chip to some extent of nanometer technology. They don't bother about considering with these things and some other things also. So that is why they design at 180 nanometer. But in here, at certain, for some specification, you have to go with the HVT and LVT because to meet the timing. What is that timing? Okay, that is to meet a timing, you need to design the thing properly. So to meet the timing, you need to alter the HVT. You need to use the HVT and LVT. HVT and LVT will change the operation of your MOSFET. So this will in turn help you to achieve the timing. So that is where STA is meant. That is static in STA comes into action, static timing analysis. So the technology varies because as the width changes, you can meet the timing. Understood? The basic thing is what happens with the nanometer technology changes is that if you are at higher nanometer technology, 180 nanometer technology, you can't achieve you can't make your processor fast. The simple way to tell is can't make your processor to work fast. But if you are at 10 nanometer technology, for example 9 nanometer technology or 5 nanometer technology, which is Apple is designing now, their processor or their task will be performed at faster speed. Means they can perform a task at very fast because of the HVT and LVT cell utilization. We can use the HVT and LVT cells and vary your timing or meet your timing. If you meet your timing, your task will be performed fast. If your task will be performed fast, your chip will be, or chip or whatever the thing will be working fast. That is the major difference, I can say. Understood?
So you are going to say that LVT cells are we use more LVT cells in low technology, right?
No, nothing like that. It's not about only LVT. HVT and LVT both. See, the thing is, HVT is that you have the threshold voltage, you are changing it to higher voltage. When it comes to LVT, you are making your threshold voltage to be low. For example, if you are you are not only going to play with the these things. This is only about chip. If you go out of the chip, you will have diodes also in your circuit. Okay, so if, for example, if you are having a IN4001, that's a diode which has 0.7 volt as a trigger voltage. So conducting voltage, that pinch of voltage. After 0.7, the diode starts to operate. So at that time, you use the LVT, where you will make the threshold voltage less than 0.7. So your chip, whatever the output of a pin, output from a particular pin of the chip will be a certain voltage, which will pass through the diode, or which will make the diode to trigger, or it won't make the diode to trigger at certain time. So these are all like pulses. For example, I'll again go back to these are all again going to be like see, this is, for example, a wave. Okay, here you consider 0 and here you consider 5. This is the basic. But when it comes to the thing, you can operate in a range where you don't need to be 0 here. You can be 0.6 for certain thing, and you can be 4.2 here. Okay, you are not.
You are sharing old screen.
Sorry. Yeah, you can see this, right? This is the 0 and this is 5. See, this can be the this is the standard what you all have learned in labs or academics. This is the practical. Means you can use like this also. This won't trigger a diode. If you are using 0.6, this won't trigger a diode. Okay. After this, it will be clipped, or the flow for diode might change. So if you are working in a circuit, what I'm saying, for LVT, you will make the threshold voltage, whatever the threshold voltage, right? This is this part. This is if you are looking at the MOSFET, this is the saturation region. This is the linear region. This is the ohmic region, right? So here somewhere it will pinch off. So you can drag this. This is the SVT, standard voltage, whatever. Okay.
Standard threshold voltage.
Standard threshold voltage, standard voltage, SVT. But when you come to LVT, you want it to trigger very early, here only. So you bring this triggering thing very early. Okay. But in HVT, you can change it to lately to be triggered. Okay, here. So this is here. This thing is where you make the thing to wait, because you are getting, see, for example, you are you have a flip flop here. Okay, you will be having two inputs. Okay, SR. Okay, SR, anything. Just consider a flip flop, or you consider a gate only. This will be easy for you. This thing is getting signal already. Okay, this thing is not getting a signal. So I'll start again from first page. Yeah, this thing is getting signal. This thing is not getting signal because the propagation delay for this is less. Okay, the propagation delay for this is more. Okay, what happens is that you will add a, before this you have a gate. So you, what you make is that you will make this a HVT cell. No, this is a HVT cell. HVT cell means before this you will put an HVT cell, or for a, HVT, if you whatever thing before this is HVT, means what happens is that in this, if you have like this, it will make you to wait. The duration of waiting for this will be the duration that the signal will arrive for this. So if the duration is 6 nanoseconds, if this thing is arriving 6 nanosecond lately, this will be made to wait for 6 nanoseconds, so that the both input for this will be at the same time, so you get a proper output. If not, for example, you might have shown in D flip flop. Okay, you might have on a D flip flop. If you give an input, you queue something. If you give an input, the data might change because it will check the previous state, right? It will consider previous state or previous inputs and gives an output, or it retains the previous. Q will be Q bar will be, Q will be 0, Q bar will be 1. Again, if you give 0 0 and again 0 1, the thing will be retained previously only. Whatever the inputs will be, that the same thing will be given here. So this will change. This will not change. So this should not happen at that particular area. You need a 1 here. So if you give at a time, it might change like 0 1 or 1 0 combination. Here, whatever if you give 1 0, it will give delayed 1 0. You need 1 0 here. Okay, if you are giving, for example, I'm considering a flip flop here. So if you are considering 1 0 here, you need 1, right? Output should be 1, something like that. So that time it won't delay much. It won't. The output will be ready, and it will give correct output. If a certain, instead of 1, if it goes 0, or for example, if I need to show in output, if it goes like, if it needs to be 1, if it needs to be 0 here. Instead, if it goes like this, and again next it goes like this, here you are gone. The thing is, circuit is gone, or the program is gone, or the flow is gone, or something is wrong here. This we call it as glitch in the thing, or this thing will happen. And if this happens, for example, if there are two signal routings, this is for here one block is connected, here one block is connected. If the glitch happens, there will be a crosstalk between these two. Means there will be a coupling capacitance here. So this will affect this. If this affects the parasitic extractions, the parasitic I showed you, right? Parasitic extraction things, those values will change. If those changes, your STA will be affected. So the main thing is LVT and HVT are only used to change or alter your delay. Or the main thing is to meet the timing analysis. It doesn't. It's not like you can't use LVT, HVT in lower nanometer or higher nanometer. But yeah, for certain nanometer technology, you can't use. You can use both the things. In certain areas, you need HVT. In certain areas, you need LVT.
So actually, the core part is used as LVT devices, I guess IO part is used with the HVD devices, right?
Nothing like that. Nothing like that. Nothing like that. See, the thing is, you don't need to worry about it right now only, because that will again confuse you. Just consider you have the words in your head that LVT, HVT. What's LVT? What's HVT? LVT is low threshold voltage, low voltage threshold. HVT is high voltage threshold. Means LVT makes the thing to trigger early. HVT makes the
No, that is not the
MOSFET
reason.
trigger lately. That's it. No. That's the thing. What's the if you are if anyone is asking you, you can say this thing. What is LVT? What is HVT? You just have that thing. When it comes to working, you need to change it. You don't need to worry right now only, because you will not understand why you use HVT or why you use LVT at everywhere. You use it everywhere, but not like in a particular technology. Use it in all the technology.
So the point explanation was about to differentiate the higher and lower nodes, right?
What do you mean with higher and lower nodes? Like, no, it's not like technological nodes. It's not about that. I just said you the way they operate. See, if you come to the lower nanometer technology, the thing here is you will have a particular person as low power IC designers.
And that is the reason, like, why we are going for lower nodes is to reduce the power consumption and area. That is a basic thing.
Power consumption, area doesn't matter, because it's not like 180 nanometer doesn't mean that your chip will be small, and 3 nanometer doesn't mean that your chip will be even smaller than that. It's not like that. The thing is, the different gap between the source and drain will be, the channel length will be modulated. That's it. Your chip doesn't vary. Don't keep that in mind that 180 nanometer and 3 nanometer will be of different size. All will be of the same size only. The thing is, technologically, these things will be faster, low power consuming. This is the things. Like, it's not with the size, and it depends on the applications also. See, you use 180 nanometer technology in a car that has that in there you need to use it to operate your music system. If you press a button, the sunroof needs to open. For certain things, if the door is not locked, it needs to indicate. If the seat belt is not worn, it needs to indicate. If these are the conditions, 180 nanometer technology is more than enough. So, but in Apple iPhone, see, if you press a button in a car, it takes certain milliseconds only and then operate. But in not the same thing is not with your phones. If you touch a phone, it needs to respond in certain millisecond gap. That you should not identify that it is delayed, right? So this is where the timing application comes. So as you go lower nanometer technology, the timing and power consumption will be less. That's it. Kamal, right? You got it? Or
Yeah, I got it.
someone else took a question. Hello. Hello. Someone Venkat or something Venkatesh took a question. Okay, fine. Anyone else, or is it okay?
Apart from LVT and HVT, is there anything changes from HVT from higher nanometer to lower nanometer?
I said, right, higher nanometer and lower nanometer, you will have these things as application wise, you will change them. The timing, the first thing what I always focus is timing. So if you want to make a particular task to happen at very less delay, or have to make it, you want to make it happen at very faster speed, you use the lower nanometer technology, and to consume very less power, you go for lower nanometer technology. If you are able to compromise with the timing and the other thing as power, you can go with the higher nanometer technology. That's it. Any more, or is it okay to end? Hello. Fine. I'll stop sharing my screen. I think I'm done here. Fine, then we'll end the meeting. If anyone has any doubts, we'll discuss. If not, then I'll end the meeting.
Sir, what are the different metal layers used in different technologies, sir? Do you know any idea?
See, the thing is, it varies on the application. Whatever the project I worked was certain metal layers, but I worked till the metal layer 7. I worked the thing is, it was 14 nanometer technology, and where it was just like a dummy project to learn. So metal layer 7 metal layers were there. The base metal layer was pins and all. The first metal layer was standard cells. Second metal layer was the VDD and VSS for standard cells, particularly for standard cells. Third was for I think macros and all. Fourth and fifth was for third and fourth was for clock tree. Fifth and sixth was for power. So routing happens everywhere. Routing doesn't need a metal layer, and for clock, third and fourth was the metal layer provided. So it's like that it varies. Even we were having more than 7 metal layers. The 7th, 8 metal layers were all there, but we were not allowed, or we were not given the access, or we were not we were not given the access to work on those metal layers, because those will be designed by the top level engineers. Top level engineers are those who start to work on the project from MRD, the market requirement documents, from there to till tape out. So they take on some certain metal layers to perform some operations. So those metal layers will not be granted. I worked on 7 metal layers of 14 nanometer technology.
Thank you.
Okay. Fine, then I'll end the meeting.